Hello, welcome. Last video in electrochemistry, and this is kind of showing a cool process. Chrome plating is done on lots of things with cars, and these are bumpers right here. You can see how they've got the chrome plating, and it's a real common process with the automobile industry, motorcycles, makes these things look cool, hot rods, people do that. So it's just an electrolysis, and electrolysis is going to go and it's going to take the chromate ion, which ends up being dissolved in solution, add the electrons here to it at the cathode, and then by adding those electrons to it, it's going to become chromium metal. So if we look at it right here, the chromium ends up being +6, so it's a +6, so we're talking about chromium 6 plus, and then +6 electrons turns into chromium metal, right? So that's what we're looking at. So what do we need to know? Well, to be able to figure out what to do here, we're going to have to figure out electrical charge, how much current this is going to take, stuff like that. And so here's what I know. I know that I want to make it 0.21 millimeters thick, and so just a real tiny thin top layer of chrome. And I know that I have a total area of 0.31 cubic meters. So what I really want to find out is my volume, because once I find out my volume, I could use my known density of chromium to figure out exactly how many grams that would take. So let's go ahead and do that. I'm going to take my millimeters and turn that into meters. So that's going to multiply times 1,000, 0.0021 meters, times my total area, which is 0.31 square meters, and this is going to give me volume because I got meters times meters here. It's essentially height times length times width here. So that is going to equal 6.51 times 10 to the -5th cubic meters. Now, I have cubic centimeters per gram, so I could convert this to meters, or I can convert the meters down to cubic centimeters. Either one would work. I'm going to go ahead and convert the meters down to cubic centimeters. So 1 cubic meter is going to equal, we've got 100 centimeters in 1 meter, right? And we're cubing that. So we have 100 cubed. So actually it's going to be a factor of 1,000,000. So if I multiply this number here by 1,000,000, I'll have this converted to cubic centimeters. So move that little decimal over 6 places, and I should have 65.1 centimeters cubed. So now to figure out the actual mass, I'm just going to have to multiply that times the density, because it's 7.2 grams per 1 cubic centimeter. And so what do I have? Well, I have a total of 468 grams of chromium. So now I know exactly how many grams, and so at this point I need to figure out how many moles that is. Well, chromium, it's about 52 grams per mole. So if I divide 468 by 52, I get 9.01 moles of chromium metal. Now, for every 1 mole of chromium metal, so here's 1 mole, it takes 6 electrons, right? So my total moles of electrons is going to be 9.1 times 6 moles of electrons, because chromium has an oxidation number of +6 in this situation. We see that right here. And so, well, so then what do we do? And one more thing, just to show you, to prove that, the chromate ion right here is actually a -2. So this is in a chromate solution. If this is -2, we've got a total of -8 here, and we have an overall -2, so this has to be +6, and then this is -8, so it gives us leftover -2. So that's assigning your oxidation numbers, and you can be sure of this +6 right here. And I just kind of use this little diagram to show you how that works. So multiply that times 6, and what do we get? Let's see, we get 54.09 moles of electrons. Okay, so 54.09 moles of electrons, and then what do? Well, we know that moles of electrons equals the total electrical charge divided by Faraday's number. So we can do that. We can take our 54.09, and that's going to equal our total electrical charge divided by Faraday's number, which is 96,485. So I'm going to be multiplying 54.09 times 96,485. So it's going to give me a total electrical charge, Q, is going to equal 5.22 times 10 to the 6th coulombs. Because remember, electrical charge is measured in coulombs. So let's go ahead and move that over there for now. So now what am I going to do with that? Well, I can use that to figure out the amount of amps I'm going to have to put through this for a given amount of time. So let's say that I want to do it quick. Let's say that I want to do it in 10 seconds. So, well, how much amperage is this going to take for 10 seconds? Well, we know that amperage, I, equals the total Q, which we just figured out there, divided by the total time. So this is easy enough. So my amperage I, which is what we want to find, is going to equal this number here divided by 10 seconds. And so remember, this equation actually uses seconds from the previous videos. So I'm going to just take and divide that by 10. It's a piece of cake. You just really have to move the decimal one place. And so instead of 10 to the 6th, we're going to be 10 to the 5th. So actually my amperage is 5.22 times 10 to the 5th amps. Okay, so that's my total amount of amps. It's my total amount of electrical charge. Well, what else can we figure out from this? We could actually figure out the total amount of work which it takes. So work, electrical work, is actually measured in watts, and 1 watt equals 1 joule per second, and so that's kind of a measure of electrical power. So 1 watt equals 1 joule per second. So what we usually use is kilowatt hours. Oops, big W. And so kilowatt hours. And so kilowatt hours equals 3.6 times 10 to the 6th joules of energy. So 1 kilowatt hour. And that's kind of how we measure electricity into your house. The electric company will actually charge you per kilowatt hour. So we can find out exactly how much we're going to use to do this process. And here's the equation that we'd use. Work, actually, the total amount of work is actually the same as the G. And remember, we learned earlier that the change in G is going to equal the number of moles times, well, anyways, I'm not going to relate that in this one right now, but I'm going to give you a new equation. It does relate to the change in G. So the work equals the number of moles of electrons times Faraday's constant times, let's see, it's got to be in my head somewhere, times, oh yeah, times the actual voltage here. So it's called EXT. So we know the volts, and this is actually the volts that we got from that Nernst equation. Remember, the Nernst equation, equals that, and then minus the number of moles and all the other things, blah blah blah. So, anyways, the Nernst equation from the previous. So what we're actually doing with this equation is we're incorporating free energy and the actual voltage at a non-standard condition. So this is going to be voltage at non-standard condition, and so that's what that is. And so we've been given that number right there. Now, what about this number of moles times Faraday's constant? Well, if you look up right here, the number of the moles equals Q times F, which means that the charge, which is the Q, right? So the Q actually equals the Faraday's constant times the number of moles. Sorry, that should be an N right there. So this right here is the same as Q. So we can just insert Q in for that. So let's go ahead and solve this. So our work, I'll do this over here. Our work equals our Q, which is 5.22 times 10 to the 6th coulombs. Oops, I drew 6 again. So times 10 to the 6 coulombs. Sorry about the handwriting on that one. And times our voltage. So our voltage is 6 volts. And so that makes our total work 8.7 kilowatt hours. Now, I quickly actually, this equation right here, of course, is going to give you joules, joules per second. So what I did was I took the joules per second and I divided it by, or actually I multiplied it, sorry, multiplied it by 3.6 times 10 to the 6th. No, sorry, I divided it by 3.6 times 10 to the 6 joules, and that gave me the 8.7. And so that's our total amount of kilowatt hours. And then what we need to do is we need to look at what does that mean for efficiency. So it says it's 75% efficient, which means that if it was 100% efficient, it would only take 8.7 kilowatt hours. So what are we going to do now? Well, if it's 75% efficient, I can take this 0.875 and I can divide it by my percent of efficiency. So 0.75, and then that's going to give me my total amount, which is going to be 11.6 kilowatt hours. All right, so this should be a small h right here. Sorry about that. So anyway, so this is actually what it's going to take, because this whole process is 75% efficient. All right, so that's kind of a little bit more complex. Sorry about the little bit of bad handwriting and skipping a few equations here and there, but I didn't want it to be too long. You should get the idea, and this should help you with some of the problems you're doing on your web assignment.